Welcome, friends, to Intro to Probability and Stats, Lesson 4.1, where we're going to talk about random outcomes. That sounds random. Sample spaces, like at the end of the aisle in Costco. I don't know, maybe. And events. Let's do it. So I made a new friend. His name's Jack. He likes me to call him Ice Pick. Anyway, he plays this game called Dice, or with Dice. It's called Poops. It's a weird name, right? And I don't get it. He says, like, I roll 2 dice, and they're supposed to add up to 7, and if not, he gets my money, and I don't know. I guess that's just how friends do things these days. Let's talk about some math lingo, some probability lingo. An outcome is the final result of an event. Well, it'll be nice to know what an event is, right? Sorry, I blew in the microphone. And in this case, with me and my buddy, rolling both dice is the event. And so the outcome would be like, what score did I get? Did I get a 6 when you add them together? Did I get a 7? That would be an outcome. So in general, an event is any experiment that has a collection of outcomes. And the set of all possible outcomes for an event is known as its sample space, which is not located at Costco most of the time. So I'm worried about losing my money, so I want to know, like, how many ways are there for me to win this game? If I roll the first die, I can get a 1, 2, 3, 4, 5, or 6. And then, let's see, in order to win the second die, if I rolled a 1 on the first die, and I need to add up to 7 to win, I would need to roll a 6 on the second die. If I rolled a 2 on the first, I would need a 5, and so on. I would need to get my dice to add up to 7. So it looks like there's 6 ways for me to win. So that sounds pretty good. I got like 6 chances of winning, right? Well, I don't know if that's good or bad. Maybe we can find out. I don't know. In order to find out, I know that there's 6 ways for me to win, but if I can find out more about the entire sample space, which is the collection of all the possible outputs for the event of me rolling a couple dice, maybe I'll have a better idea if this is a good game or a bad game for my bank account. So when I roll the first die, there are 6 possible outcomes. When I roll the second die, there are 6 possible outcomes. And so all I would need to do is, kind of add up all of these, and that would be my score. So if I roll a 1 and a 1, my score here would be a 2. If I roll a 1 and a 2, my score here would be a 3. If I roll a 1 and a 3, my score would be a 4. If I roll a 1 and a 4, and so on. And so that's if I rolled a 1 with the first, and then I combine that with each of the second possible values I could get on the second die. It's so weird that it's a die, that the singular of dice is die. I just feel weird saying it, so I apologize if I sound weird saying it also. So if I roll a 2 on my first die, that can also be combined with every other possible score for the second die, and so on and so forth. And if we add together all the dice totals, we get a nice little chart like this. So these are the possible scores. So how many total are there? There's like 6 across and 6 down. So there's 36 different outcomes, and only 6 of them, 1, 2, 3, 4, 5, only 6 of them have me winning. So that's not awesome. I got a 6 out of 36. That's a 1 out of 6 chance of winning. Not cool. Not cool, Ice Pick. So rolling 2 dice has a relatively small set of outcomes, like a relatively small sample space. What about if we get into some bigger situations, like getting dressed in the morning? Let's say you got 15 shirts, 10 pairs of pants, 8 pairs of shoes. How many outfits can you make? So here's 15 shirts, 10 pants, and 8 shoes. This is actually how my clothes look. I just have 15 white shirts with the numbers 1 through 15, and then on the right leg of each pant right pant leg, I have a large number written with a magic marker. Same with my shoes, and the number does hang off like that a little bit. Let's say, so I got 15 shirts to choose from. Let's ignore shoes for now. Let's just look at shirts and pants, and then we'll bring shoes back into the mix a little later on. Let's see. Let's say I pick shirt 1. So if I'm wearing shirt 1, I can still pick any one of these 10 pants, right? So that's 10 outfits just off of that one shirt. So here's them. Then what if I pick a different shirt though? What if I pick shirt 2? I could still combine that with any one of these 10 pairs of pants for another 10 different outfits. So none of these, there's 20 outfits down here now, none of them are the same. Well, I can keep repeating that process for each shirt. So for each shirt, there's going to be 10 different outfits because I can wear it with 10 different pairs of pants. So I'm going to take 15, the number of shirts, times 10, the number of pants, and that's going to give me 150 possible combinations of shirts and pants that I could wear. We call that the multiplication principle of probability. If you're picking one out of this set and one out of this set, then if there's 15 here and 10 there, you do 15 times 10 to figure out the possibilities. All right, so here is a representation of those 150 different outfits. Now, remember there were shoes. So for each one of these outfits, I can pair that with 8 different, one of 8 different pairs of shoes. So every one outfit up here, once I combine it with shoes, now we're talking about there's 8 outfits for each one of these pant and shirt combinations. So I'm going to take the 150 pant and shirt combinations and I have to multiply that by 8. So altogether, there are 1,200 or 1,200 combinations of totally awesome outfits that I can wear to school. Man, I got a big closet. I didn't realize that. So rolling dice and tossing coins are good ways to make random choices. But what if you do both? Then what happens? Let's see, how am I going to do both of these? How many possible outcomes are there? That's a good question. So let's see, when I roll a die, I can get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And then, if I flip a coin, then say I rolled a 1, and then I flip a coin, I can get a heads, or I can get a tails. Same thing if I rolled a 2, I can still get a heads or a tails. 3, same thing. And so on down the line. And there are 6 possible choices here, and 2 possible choices there. So the multiplication principle tells me 6 times 2 is my total number of possible outcomes. So I should have 12 possible outcomes, and if I look over here I can figure out exactly what those 12 outcomes are. A 1 and a heads, or a 1 and a tails, a 2 and a heads, or a 2 and a tails, a 3 and a heads, or a 3 and a tails, and so on down the line. And you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them. So yay, the multiplication principle totally works. Alright, here's a crazy one. A family has 3 members. We will call them A, B, and C. They belong to a clinic with exactly 3 doctors, and we will call them 1, 2, and 3. Each family member went to the clinic last week. The doctor they saw was randomly assigned each time they visited the clinic. So A is how many different outcomes are there for the family if each member went to the clinic exactly once. So let's look at person A. Person A, when they went, they could have had Dr. 1, 2, or 3. So that means A with Dr. 1, A with Dr. 2, A with Dr. 3. Then B, when B went, they could have seen Dr. 1, 2, or 3. So going down this road would say A went to Dr. 1 and then B went to Dr. 1. Here this one says A went to Dr. 1 and B went to Dr. 2. Here this one says A went to Dr. 1 and B went to Dr. 3. Well, we have B still has those same three options regardless of which doctor A went and saw. So we get this like this tree building kind of a thing. We call this a tree diagram. Well, so if it was just A and B, we already have 1, 2, 3, 4, 5, 6, 7, 8, 9 options. But C also went. So under each one of these, we could have A went to Dr. 1, B went to Dr. 1, and then C can go to Dr. 1, 2, or 3, and so on down the line. So there's all these different possibilities, right? A could have went to Dr. 3, and then B went to Dr. 3, and then C went to Dr. 3. So there are 27 possible outcomes right here. So there's the answer to A. There are 27 different outcomes. And then B, in how many different ways could all three doctors be seen exactly once by a member of this family? So that means if A went to Dr. 1, then we can't count anywhere B went to Dr. 1. Can't go to the same doctor. So we're only looking at B2 and B3. And we can't look at anywhere C went to Dr. 1. If we're looking down here, A1 and then B goes to 2. C would have to go to 3, right? Because doctors 1 and 2 have already been gone to. One thing that I like to do is under my tree diagram, I'll actually write what the outcomes are. So this outcome right here, following this path, is A went to Dr. 1, B went to Dr. 1, C went to Dr. 1. Under the C2 here, it's A went to Dr. 1, B went to Dr. 1, C went to Dr. 2. And then under this guy, the C3, it's A went to Dr. 1, B went to Dr. 1, C went to Dr. 3, and then you kind of just follow that pattern out. And what I can do now is I can just look to see the doctors are my numbers, so I need to see the outcomes that have all three different numbers. So if a number repeats itself, that means a doctor saw two members of the family. So I'm going to look through and see, look, here's one where they all saw different doctors. Let's see, there's another one where they all saw different doctors. Each doctor sees one member of the family. There's one. Each doctor sees just one member of the family. Here, same thing. Next one's right here. Next one's right here. And if you look carefully, the rest of them have at least one doctor seeing two different members of the family. Not cool. So there's only 6 ways out of those 27 where all three doctors see exactly one member of the family. Cool, huh? All right, let's look at some examples. During spring semester, a student has to choose a science elective and a free elective. So, options for science electives are electronics, earth science, and psychology. So there are 3 options for the science one, and then the free electives are the art of comedy, there's 1, anthropology, there's 2, and home economics, there's 3. Students who do not request the electives they want will be randomly assigned 1 science and 1 free elective. So if a student is randomly assigned to a science and a free elective, how many possible outcomes are there? Well, there's 3 of each, so I'm going to pick 1 out of these 3 and 1 out of this 3. The multiplication principle tells me 3 times 3 equals 9. So that one is 9. There's 9 possible outcomes, 9 combinations of elective classes for that guy. What about Julian? He decides to take anthropology, so that takes care of his free elective. He will be randomly assigned one of the 3 science electives. How many possible outcomes are there for him? Well, he's already got anthropology, and then So it can be anthropology and electronics, anthropology and earth science, or anthropology and psychology. So there's only 3 options for that guy because he picked one of these. What about flipping a pizza? Nobody likes that. Aaron Rodgers doesn't like that. Look at him. He's like, what'd you do? Come on, it's a pizza! Archery. 2 archers are competing against each other. They each shoot an arrow 3 times at a target with 4 rings on it. 20 points are awarded. Here's the picture. Okay. 20 points for there, 15 for there, 10 for there, 5 for there. Yeah, there's lots of words to read, but whatever. Scores must be unique, right? A 5 and then a 5 and then a 10 is different from a 5 and then a 10 and then a 5, right? So it's like arrow 1, arrow 2, arrow 3, arrow 1, arrow 2, arrow 3. It's not just what's your point total. What is the size of the sample space of scores that one archer could receive with 3 arrows? So if he's shooting 3 arrows, the first arrow has 4 different options times the second arrow has 4 different options times the third arrow has 4 different options. So 4 times 4 times 4 is 64. All right, so now we're going to talk about like what type of events we have. What if you tossed a coin and rolled a die, but you wanted to get a heads and a 6? That would be a simple event. There's only one way to get a heads and a 6, right? A heads on the coin and a 6 on a dice. There's only one way to get that. That's called a simple event. What about a basketball player shooting some free throws? Let's say he shoots 4 of them. He can make all 4. He can make 3 out of 4. He can make 2 out of 4. He can make 1 out of 4. Or he can miss all of them, which would be really sad for him and his fans and his parents and his sister. Okay, so, but what about which ones are simple events? And which ones are complex events, compound events? The simple events are making all 4, missing all 4. There's only one way to make all 4 of your shots, or to make all 4 of your shots down here. You got to make all 4 of them. There's only one way to miss all 4, and that is to just miss all 4 of them. So those are simple events that only have one way of happening. A compound event is there's multiple possible ways it could happen. So making 1 out of 4. That you could have made the first one, you could have made the second one, you could have made the third one, you could have made the fourth one, right? But so that counts as 4 different ways to only make 1 shot. Either way, you're missing 3, only making 1. But it's which one did you make, right? There's 4 different times when you could have made the 1. Same thing with 3 shots. That means you're gonna either miss the first one, second one, third one, or fourth one. So there's 4 different ways to make 3 shots. And then there's even more ways. There's 6 ways to only make 2 shots. So these are your simple events, and the rest are compound events. Simple events, there's only one way to get it. Compound events, there's more than one way to successfully shoot 1 shot. All right, so let's look at some questions here. Bob rolls 2 dice and gets double 6s. Jim flips a coin 3 times and gets 1 heads and 2 tails. Gus flips a coin 3 times, gets 3 heads. Ned rolls a die twice and gets the same number each time. So Bob rolls 2 dice and gets a double 6s. If he's rolling 2 dice at once, there's only one way for this one to be a 6 and only one way for this one to be a 6. So this one is a simple event. Jim flips a coin 3 times, gets 1 heads and 2 tails. Well, he could have went heads, tails, tails, or he could have went tails, heads, tails, or he could have went tails, tails, heads. There's 3 ways to get that, so that is a compound event. Gus flips a coin 3 times and gets 3 heads. Well, there's only one way to get heads 3 times, and that's just getting heads, heads, heads. So that's a simple event. Ned rolls a die twice and gets the same number each time. You might jump on simple for that one, but you could have got a 1 and a 1, Or you could have got a 3 and then a 3, or a 2 and then a 2, or a 4 and then a 4, or a 5 and a 5, or a 6 and then a 6. So there are 6 ways to get that. So that is a compound event. So which of these are simple events? A student receiving A's on his first 3 tests. So those are all the same. So that is a simple event. A student receiving A's on 2 of his first 3 tests. Well, if he got A's on 2 of them, he could have went A, not an A, or he could have went A, not an A, and then an A, or it could have, instead of being a B, it could have been an F. There's a bunch of different ways that he could do that, so that one's compound. Flipping a coin and having it come up heads. There's only one way to do that. Flipping a coin and having it come up tails. There's only one way to do that, so that's simple. Flipping a coin and having it come up heads or tails. Well, there's 2 ways, heads or tails. So that is a compound event. So A, C, and D are the simple events in this guy. A student can take 1 elective in the spring semester, choosing among 4 classes. For each of the 4 classes, there are 2 different teachers. Uh-oh. How many leaves would there be on a tree diagram? Well, there's 1 elective, and we're going to choose one of 4 classes, and then we're going to choose 2 teachers, so 4 times 2 equals 8. 8? There would be 8 leaves on such a diagram. Oh my goodness, that's the end of the lesson. You made it. Congratulations. You're the big winner. Raise your hand. Who's the big winner? Who's the big winner today? You are. That's right.